Hello everyone, Shu Yan here. The paper today is Composable Deep Reinforcement Learning for Robotic Manipulation from Berkeley Artificial Intelligence Research Group. The neural network has proven its capability to acquire complex behavioral strategies. However, it remains challenging to apply neural networks in robotic control problems due to the high sample complexity. In this paper, we're going to see how the authors apply soft skill learning in real-world robotic manipulation and how they compose a number of policies for a more complex task. Model-free deep reinforcement learning has shown its capability in video games and robotic manipulations. The two state-of-the-art approaches are NAF and DDPG, which are also used as baselines in this paper. Gu et al. Use NAF to learn door opening and reaching by parallelizing across multiple robots. NAF represents for normalized advantage functions. It considers a Q function that is quadratic with respect to the action. It learns the exact maximum, and thus the policy is deterministic. Verseric et al. Employs DDPG for robotic manipulation with example demonstrations. DDPG stands for Deep Deterministic Policy Gradient. It learns a deterministic policy and a Q function. The policy is trained to maximize the Q function, while the Q function is trained to represent the expected return of a policy. However, these model-free methods are known to perform poorly when the interaction time with the environment is limited, which opposes our desire for the real-world robotic task. For some scenarios, the training time is an important factor. We would like a robot to learn in a short period of time and demonstrate high accuracies. The authors try to address this problem with soft Q learning. SQL is based on the maximum entropy reinforcement learning. The standard RL objective seeks a policy that maximizes the expected rewards. But in the soft Markov decision process, we seek for a maximum entropy policy, aka an entropy regularized policy. The authors address the robotic control problem with SQL for two main reasons. The first reason is that SQL learns a multimodal exploration strategies. Instead of learning a deterministic policy, SQL learns a stochastic policy via Boltzmann distribution, which naturally balances the exploration and exploitation trade-off. The second reason is that policies learned with SQL can be composed together for a more complex goal. Independently trained maximum entropy policies can be composed together by adding their Q functions, which yields a new policy for the combined reward function that is close to the corresponding optimal policy. It is worth mentioning that the policy composition process is offline, which means that there is no need to interact with the environment again. Compositionality improves training efficiency as it composes existing skills without further online training. It provides reusability and enables quick initialization of policies for learning complex compound skills out of previously learned building blocks. While simply adding Q functions does not generally give the Q function for a combined task, the authors show that the regret from using the policy obtained by adding the constituent Q functions together is upper bounded by the difference between the two policies that are being composed. Intuitively, if two composed policies agree on an action or if they're indifferent towards each other's actions, then the composed policy will be closer to the optimal one. A compound task can be expressed in terms of the sum of the individual rewards. The conventional approach is to solve the compound task by directly optimizing this compound reward for every possible combinations. However, the number of combinations is exponential. Compositionality makes this learning process much faster because it allows to train an optimal policy for each reward and later combine them. To combine policies, a simple approach is to approximate the true optimal Q function with the mean of individual Q functions. In conventional reinforcement learning without entropy regularization, we cannot make any guarantees about how close the combined Q function is to the true optimal Q function. But now, with maximum entropy policies, the authors prove that the difference between these two Q functions are upper bounded. Essentially, as per the lemma here, the simple additive composition of Q functions never overestimates the optimal Q function by more than the divergence of the constituent policies. Thus, the true optimal Q function is bounded by the constituent ones. But it does not necessarily mean that the composed policy will have a higher value. To that end, the author used soft policy evaluation to bound the value of composed policy. The theorem essentially states that the bound becomes tight if two policies agree in states that are visited by composed policy. While this bound is likely quite loose, it does indicate that the regret decreases as the divergence between the constituent policies decreases. The proposed SQL approach demonstrates better sample complexity and fast, reliable learning. The authors experimented in both simulated and real-world robotic manipulation domains. For the simulated task, musical physics engines used, and for real-world experiments, a Sawyer robotic manipulator with 7 degrees of freedom is used. Baselines contains the two state-of-art approaches, NAF and DDPG. We're going to investigate 4 tasks, namely pushing, reaching, Lego block stacking, and stacking plus avoiding. First, let's see how SQL performs in the simulated environment. The constituent task requires a planar arm to push a cylinder to specific positions along one of the 2 axes, which is essentially the same example we had before. Here, we can see the robot is trained to move along x-axis and y-axis separately. Then, the combined policy pushes the cylinder to the specified position. No additional samples from the environment are used to train the combined policy. The policy learns to satisfy both original goals rather than simply averaging the cylinder locations. No additional samples from the environment are used to train the combined policy. The combined policy learns to satisfy both original goals rather than simply averaging the final cylinder locations. Now, let's look at how the proposed SQL perform in real-world manipulation. In the first task, reaching, we investigate the sample complexity. As the figure shows, SQL solves the task in about 10 minutes, whereas DDPG and NNF are substantially slower. In the second task, the robot is required to stack Lego blocks. It takes half an hour for the robot to insert the Lego block for the first time. In 2 hours, the policy converges with a 100% success rate. The resulting policy does not only solve the task consistently, but it also surprisingly robust to disturbances. To test the robustness to disturbances, the robot arm is forced to be in an uncommon state. The policy was able to recover every time and eventually solve the task. The robustness can be attributed to the effective and diverse exploration that is natural to maximum entropy policy. The third task focuses on compositionality. The robot needs to stack the Lego block, meanwhile avoiding the obstacle. A separate policy for avoiding a fixed obstacle is trained. Before composing these two policies together, let's see how they perform on their own. The avoidance policy was able to bring the Lego block close to the target block, but never successfully stacked the two blocks together. The stacking policy collides with the obstacle every time, but was still able to solve the task 30% of the time by chance. Now, let's go ahead and combine the stacking policy with the avoiding policy. The combined policy successfully avoided the obstacle and stacked the block every time. To conclude, we explore how soft skill learning can be extended to real-world robotic manipulation. We have seen that XQL substantially outperforms prior model-free reinforcement learning in simulated and real-world environments. The method proposed in this paper exhibits better stability and convergence, and the ability to compose Q functions obtained via soft Q learning can make it particularly useful in real-world scenarios, where retraining new policies for each new combination of reward factors is time-consuming and expensive. That's the end of this video. Hope you enjoyed. Bye bye.